I'll be characterizing TGS, Triglycine Sulfate, that is. I am Charmaine Brianne Williams. I'm from Jackson State University, here at the REU program for the summer at the University of Alabama, AAMU. My objective is to grow TGS crystals doped with sodium chloride in an attempt to increase the ferroelectric properties of TGS and increase the strength of the material concurrently. These are some of the questions that I will be answering. What is TGS? What is sodium chloride? What does it mean to be doped? What are the uses of this compound? What does this doping procedure consist of? What's dope? And also other intricacies of this compound. Glycine is an organic compound. This is the chemical formula, which does not, the empirical formula, which does not actually match the structure of this molecule. It's very important to remember. It is 2 hydrogen atoms at its side chain. Glycine is the smallest of the 20 amino acids. It was discovered in 1820 by Henry Braconnot by boiling gelatin with sulfuric acid. It is biosynthesized in the human body from the amino acid serine, which is a polar amino acid. It lacks an internal plane of symmetry. There's no superimposable mirror image. It's manufactured industrially for treating chloractic acid, which is an orgochlorine compound with ammonia. It's a non-chiral proteinogenic amino acid. That means it's found in proteins. And the physiological function is a precursor to proteins. Sulfuric acid. It's a strong mineral acid. It's soluble in water at all concentrations. The historical name vitriol was given by the Sumerians, and it basically was called oil of vitriol because it's very viscous and clear liquid. So it was much so compared to oil. The principal uses are listed here. It is produced in the upper atmosphere of Venus by the sun's photochemical action on carbon dioxide, sulfur dioxide, and water. It uses autopropylysis as it dissociates through protonating itself. It is highly electrical conductive, sorry about that mistake there, and its dielectric constant is around 100, very polar and available in many purity grades. Triglycine sulfate. That's 3 moles of glycine with 1 mole of sulfuric acid. It's a chemical compound. Here is its empirical formula. It contains protonated glycine moieties and sulfate ions. Moieties. This means this is the important part of this compound. It's pyroelectric and also ferroelectric. In the polar space group, that just has to do with its monolithic lattice system. That's just basically the shape. As I was telling you in my last presentation, with it being a base, being A axis, C axis, B axis coming straight up. And it's very hygroscopic. Again, hygroscopicity is related to how easily, because it's polar, how easily it can be broken down by water, just as easily as it's built up by water. And as you can see, this is the structure of such. And again, A axis, C axis, B axis going straight up. It's very important to notice how the molecules are arranged here. As you can see, G2 is consistently separating the G1s that you see here and G3s, which are listed here. The crystal structure consists of sulfuric acid, G1 and G2, and the crystal structure diagram. The species is held together by G3 with hydrogen bonds. Along the B axis, G1 sulfuric acid, sulfate, and G2 and G3 layers are stacked alternatively, as you can see here. Ferroelectricity was discovered in 1920, discovered in Rochelle salt by Bachelet. This material does not necessarily contain iron. That was very important to say because, as you can see, first word ferro meaning iron. They don't necessarily contain iron. Very important to remember. The property of a material to have spontaneous electric polarization is the definition of ferroelectricity, and I am dealing with a ferroelectric compound here. And it implies hysteresis. That is basically, it can, like your RAM in your computer, it can hold memory. And I was hoping to get into that in my presentation as well and in my research to see exactly the capacity of the memory that can be held. It can be used as a capacitor with tunable capacitance. Different levels of the capacity, we can change that, of course. Ferroelectricity is important here because it is also a pyroelectric material. And that is the ability of a material to generate a temporary voltage when heated or cooled. Even though it does have a certain voltage when it's not heated or cooled, but given at 50 degrees Celsius temperature, it does have these spontaneous dielectric moments or these spontaneous polarization moments. So it is pyroelectric, not necessarily at all times and not necessarily when it is heated or cooled, but just important to know that it is. As the positions of the atoms are rearranged, polarization is apparent. It does happen. Pyroelectric crystals generate electricity when heated. Like I said, this one doesn't necessarily have to be heated to generate electricity. Positions of, passive infrared sensors are often designed around pyroelectric materials and also ferroelectric materials. And pyroelectricity is relative to ferroelectricity, as we found that it is present in these crystals concurrently. And I've also noticed through my research that within other materials, they do coexist. So in relation to ferromagnetism, which is used as an analogy to pyroelectricity and also ferroelectricity because it's present as well. These are the growth methods of TGS. I will be using a low temperature solution for my growth. The others are irrelevant towards my research, but melting is also a very popular method in my level of research. I don't necessarily, and also top-seeded solution as well. I don't necessarily need to be dealing with the Solowski technique and the Bridman-Stockberger technique. It's just not time for me to, I don't have the time that it takes to learn the intricacies of the machinery available in my laboratory. Doping agent, and dope. A dopant or doping agent is a trace impurity element inserted into a substance at very low concentrations in order to alter the electrical or optical property of named substance. So, like I said in the beginning, I will be working to alter the electrical properties of this material. Not so much the optical properties. Mixing TGS with sodium chloride. Sodium chloride as a crystal salt, it gives this cloudy type of view as far as the optical output. So I can't necessarily say that it's to improve the optical properties, because if so, I wouldn't be using sodium chloride. Sodium chloride, table salt. Halides, that's also another word that I've learned that is also used for salt. It is an ionic compound. The salt most responsible for the salinity of the ocean, extracellular fluid of many multicellular organisms, also used as a food preservative, forms crystals with face-centered cubic symmetry. So in this case, we will not get that, as we talked about earlier, where it had no superimposable mirror image. This will allow that superimposable mirror image to exist. Used for windows, prisms, based on its optical component. It's not very reliable because, like I said, it does give a cloudy view when we want to use it for optical applications. Applications of TGS doped with sodium chloride. Fabrication of the detector element in infrared spectroscopy. Pyroelectric Vinicon tubes, a semiconductor, ferroelectric capacitor, memory storage, and piezoelectric applications as well. And yes, it is also a piezoelectric material. We've gone over a bit earlier what piezoelectric material was, so I didn't go in depth with that. A summary. This is a portion of the background information in reference to TGS, structure and characterization of this compound, present with material to be engineered. The next step includes, but is not limited to, the growth of TGS.